Welcome back, everybody. Hoping you're having a good week, start of the week. So as we promised on Monday, we are going to mainly deal with the midterm today, but I wanted to use the first 10-15 minutes to actually wrap up what we said about harmonic oscillations and also prepare a little bit for what will come after spring break. And then we are going to just deal with the midterm. Shu Yu is going to take care of the people online, and we will do the same on Friday. And Abby comes in at roughly 4 o'clock because she has classes till 4, and then she will also join either online or in person here. And feel free to eat cookies and so on. You need some energy to solve the midterm now. Okay, guys. I'm just going to switch back to both a little bit the slides and the whiteboard, and to remind you of what we did on Monday, because we are going to start from that point after spring break. So let me quickly do that. And the code which you will find in the lecture notes, if you scroll down here, you will find a code which implements the solution of both damped oscillations and driven oscillations. The driven oscillations is something we will go through in detail after spring break, but I just wanted to sketch the solution here. And in the code, which you see here, this is a simple code, and it implements the Euler-Kromer method. And I just wanted to mention this in connection with the midterm, because you're being tasked with checking if energy is conserved or not. So if you use Euler's method, which what it means is that this term V of I plus 1, which you see for the, let me increase the fonts a little bit so that you see better. Oops, let me just increase the size here a little bit. So that should be better. So if you look at the update of the position, if you take the standard Euler's method, you would just plug in the velocity at a time step I. If you now plug in the velocity at a time step I plus 1, as we discussed last week, that's going to be an algorithm which conserves energy. And you will see that when you run the calculations. There's another thing you have to be a little bit careful with when you analyze your results. So for one of the starting or the initial values in part 1, and also when you're looking at the part 2, where you have this potential which peaks very much at a certain point, what you will see then is that the solution will depend on the size of the time step which you've chosen. So you may get solutions which don't make sense, but then you should go back to the code and simply check whether the time step variable you've chosen is a good one or not. So just remember this, that there is a time step which you have to choose, and your numerical solver is an approximation to the continuous equation. And you've truncated the Taylor expansion at the level of the first derivative, which means that the error goes like delta t for velocities, and if you use Euler-Kromer, it goes like delta t squared for the position. And that will clearly influence your results. So if you get something which does not make sense from your intuition when you plotted the energy diagram or the potential, if it doesn't make sense, then you should go back and test delta t. And this applies something which is particularly important when you come to the last part, because there the potential and you're checking energy conservation, so energy as a function of time. The potential peaks very sharply at a specific point. And that means that its derivative, which is the force, is pretty large. And it will fluctuate a lot, which means that when you have a very large value of delta t, you may not see energy conservation. So keep this in mind. This goes back to this connecting the dots between computational science and numerical mathematics and your physics analysis. So you're going to see that you have a conservative force in the midterm. And that means that when you test energy conservation as a function of time, energy should just be as flat as, well, we always tease the Danes in Norway because they tease the Norwegians as a kind of neutral thing. So we always say that if something is flat, it's like Denmark seen from the sea, because the highest mountain in Denmark is something like 300 feet. Or you could say, as the Netherlands seen from the sea. Actually, the Netherlands are below sea level. Perhaps that's why the Dutch people are the tallest people in the world, right there. There's a curious thing. I don't know if you noticed that. In Western Michigan, we had many people from the Netherlands which settled Western Michigan, and they're among the tallest people in the US also. That's quite interesting. Okay, just a digression. Okay, I just wanted to bring back the equations which we looked at last time. And these equations are equations which we will pick up again after spring break. But let me just do that. And then we move over to the solution of the midterm and work on the midterm. So the type of equations which we have been looking at are equations which normally lead to harmonic oscillations. That means that we get a periodic function. So where we started was with an m, and then we had, since we were just in one dimension, but there's no problem in moving to 2 or 3 dimensions. So we had a velocity term of dx dt, and then we had the linear term, which went like k times x. And one thing which we could add now could be a force, which then is going to dampen the damping term from the velocity dependent term. And this would now depend on a frequency, its own frequency. So this is just one typical example. Now, this is also an equation which we can solve analytically. Now, one of the reasons why I bring this type of equations up is that probably you have seen something similar when you took physics 184 and you looked at specific electronic circuits. And there's one circuit which actually give you an equation which looks like this one. So that means that when you then scale away the different parameters, you will get equations or a solver, which you then can apply to a course in electronics. So let me just show you the similarities. So this is a typical equation which you will have for a driven applied force. If you take away the driven force, the driving force, then you get the general solution, which we have discussed in terms of cosines and sines. If you apply this specific force, then you will get a particular solution or special solution, as you probably have encountered in courses in mathematics when you've been discussing the solution of differential equations. So that means that every such specific course will lead to one particular solution. So the general one is when you put the right-hand side equal to 0, and then you have the particular or special one. So we are going to solve that one next week. But now I just wanted to summarize a little bit of what we did. So you have similarities here, which are pretty neat. So we have a similarity with electronics. And this is a circuit which is called RLC. And you've probably seen that when you took physics 183. So you would have a resistance here. And then you would have a capacitor. And that has a charge which depends on time. And then there is a current, I of t. And then you have an inductance, L here. And then you have some potential here, which is driving everything. And we know that the charge, Q, as a function of t, when we take the derivative of that one, of dq dt, that gives us the current. And you probably see in this differential equation, but you get a differential equation which looks like d second derivative, dq dt plus, and then you have a term which obviously deals with the resistance, like you had the velocity dependent resistance term, which goes like dq of dt And then, so here's a capacitor, and then you have a plus, a current or a charge, Q, divided by C equal to 0. Or alternatively, you could put a force on it, cosine of omega of t. Have you seen this equation before? When you took 184? So this equation here, when you scale away the different constants, it's going to look exactly the same as our driven harmonic oscillations. And that's pretty neat. So that means that you can actually reuse the codes which are developing now to solve a totally different physics problem. And that's the kind of abstraction which we want you to have with us when you solve things numerically. Because again, you have this one code to rule all cases almost. And you can then apply this to different types of motion, or you can look at the electronics. The other thing you can do is that you can look at a mathematical pendulum, and then instead of x, you would have something which goes like sine times theta. And that is suddenly a non-linear equation. So let me just bring up the solutions which we did. And you see now, when you see this equation here, you see why scaling is so important. So one of the things which we did when we look at the equations was to scale them. So we introduced a dimensionless time, which was given in terms of this natural frequency times time. And this natural frequency is now determined by k divided by m, like that. And this term called the natural frequency is the term which we then want to compare with the specific frequency which we have here. So the driving force has a specific frequency. And we saw last time that when we apply the force, after some time, all the initial conditions and the parameters which define the original system are forgotten. And the only thing which dominates the behavior of the system is the external driving force and the frequency of this external driving force. So we saw last time that we had some motion which was governed by the system parameters, the mass of the spring constant, and so on. But then after some time, the force took over. So when we scale now, if we now look at this force term, what we would do then, if we take that one, so we have an f of 0 times a cosine of omega times t. So if we introduce this term tau, we can actually rewrite that one in terms of an f0 over cosine. And then we have just an omega tilde times tau. And where this omega tilde is simply the old frequency divided by omega 0. And that simplifies also the analysis of the equations. So let me just bring up the final scaled version of the equation. So what we have is an m, and then we got this omega 0 squared because we plugged in t is then equal to this tau divided by omega 0. So we got an omega 0 squared, and then we had a dx and d tau. And then we got plus a parameter b times this omega 0. We get a dx of d of tau. And then we have this parameter here, which is plus k times x. And this is now, when we divide by m, this would then be given by this term omega 0 squared. And this is equal now to f0 of cosine of omega tilde times tau. And then we divide by m and omega squared. And we know that k divided by m is equal to omega squared. And what we got then was the following equation, which runs like dx d tau plus, and then we introduce this parameter gamma, and then we have a dx of d of tau, and then we have plus x now, and we are going to have a term which goes like f0 tilde times cosine of omega of tau, and this term f0 now is the scaled amplitude which is given by m divided by omega 0 squared. So keep in mind that this cosine is just a special force which we applied. It could be a sine, or it could be another type of signal. And we will see examples of that after spring break. And in our case now, we defined also this gamma, which was simply equal to B divided by mass and divided by omega squared. No, it's not omega squared, but omega, and times 2 here. And then what we found was that the solution with x, or if we put now this f0 equal to 0, then we found that the solution x of tau was given now by a constant a1 of e of r1 of tau plus a constant a2 of e of r2 of tau. And this r1 was then given by, and just let me quickly remind you what we had. And this R1 was given by minus gamma, and then it had plus gamma squared minus 1. And then R2 was minus gamma of gamma squared minus 1. And we got 3 cases depending on the value of gamma. We got underdamping, critical damping, and overdamping. If we now add this F0 and assume that that is different from 0, and this is where we are going to look at what we're going to do after spring break, we're going to derive it. But now I'm just going to give you the solution, and I hope you don't get offended if you just get the solution, because then we can have something to look at after spring break. So what we can get then is that this x tau now is going to be equal to the original a1 of e of r1 of tau plus a2 of e of r2 of tau. And then it's going to have a particular solution, xp of tau. And this xp of tau, due to the fact that we have a cosine solution, this is going to be given by a constant d multiplied with a cosine of this frequency omega of tau minus a constant delta. And this is what we are going to show after spring break. So this d gets a little bit more complicated expression. So it's going to be f0 divided by these frequencies which we have, 1 minus omega squared plus 4 times omega squared of gamma squared. And this parameter delta, which we also will derive later, is inverse tan of 2 times gamma of omega of 1 minus omega squared. But this is a particular solution which you get due to the fact that you have applied an external force which runs like a cosine. If you had a sine, this term would look slightly different. But the thing which is interesting, you can see now in the denominator, if this omega tilde, which is the ratio between the frequency you apply from the force and the natural frequency of the system, if that is equal to 1, what you will see then is that you can get a d factor which reaches its maximum value. And that's going to give rise to something which in physics is called resonances. So when your system resonates with the natural frequency of the system, and that has often quite some consequences, especially if you want to damp the motion on a gravel road and you're biking over a washboard. And if your bike then resonates with the washboard, then that I can guarantee you it's not very pleasant, especially if you don't have any damping on your bike. Just ask me. It happens to me every time. Okay. By the way, have you ever, there's actually a lot of interesting physics on how these washboards actually arise. And people have actually simulated that and tried to create models for how washboards are created on gravel roads. That's just an interesting physics digression. There's a lot of interesting things to study. Okay, so what I want to do, this was a way to just conclude what we did on Monday and then point to what comes after spring break. And then after spring break, we're also going to look at the two-body problem with the gravitational forces, so that we can prepare the ground for the next midterm, which I hope you will like to do, is about the solar system. So I tried, we had a vote last year and everybody wanted to keep it. Okay, should we just switch over to the midterm? Is that okay with everybody? So I'm just going to stop the recording, and then Shu Yu will take care of people online, and Abby comes roughly 4, and I will just move around here. So let me, for those of you online, Shu Yu is going to answer questions about the midterm. So, whereas I will just discuss with the people which are present in the hall here. And I'm going to stop the recording now.